Okay, so next we have Daniel Savenkov, Senior ML Engineer at JetBrains. Daniel will be presenting Beyond Autocomplete, Local AI Code Completion Demystified. In this session, Daniel will dive into the development and motivation behind JetBrains' Local AI Code Completion released in April 2024. He will discuss the advantages and challenges of running language models for code on the user's machine versus in the cloud. Daniel will cover the key components of AI code completion, including offline and online evaluation, prompt construction, and smart suggestion filtering. He will also provide insights into the rapid advancements in efficient language model inference, the team being behind the project, model sizes in production, and the costs involved in training. Please welcome Daniel to the stage.
Hi everyone, I'm happy to be here, happy to see you all. Today, I will talk about the new feature that was released by JetBrains in April this year, which is local AI code completion. My team was responsible for this feature, and today I will share with you some of the interesting details about the feature's internals, as well as some of the design choices that we had to make while developing the feature. But first of all, what is JetBrains? JetBrains is a software development company. Main product by JetBrains are IDEs, integrated development environments for software developers. There are many of them, and the majority of these IDEs are equipped since April with out-of-the-box local AI code completion experience. And that is the topic of today's talk. I will start with giving a brief introduction what is AI code completion nowadays. Then I will give a bird-eye view on this new feature that we released, trying to explain why this feature is special. Then we will go and dig into those details and design choices that I announced. And lastly, I will talk a bit about the team. So let's dig into it. AI code completion. Here is an example of GitHub Copilot. You type some code, you get a suggestion in form of this gray text. And if you like it, you just hit tab and have it inserted into your IDE. How do these features usually work? These features use large language models, and by using large language models, they need a cloud server with a powerful GPU to operate. A typical workflow is depicted here on the slide. You are typing some code. Code is sent to the internet, to the cloud. Their language model generates suggestions for you. They are sent back and displayed in IDE. This workflow is quite popular, quite widely adopted. And of course, as usual, it has its pros and cons. Let's discuss them. Speaking about the pros, you can use really big models here because you have your dedicated server with a powerful GPU inside. And that's the nice thing. Another nice thing that there are no additional computations involved on user side. Everything about model inference is happening on server, which is super nice. However, there are some drawbacks here. First of all, your code is sent somewhere to the internet, and it's clear that that is not something that anyone and every company could tolerate due to the security reasons. Also, the latency will not be super good because sending the data back and forth via internet is not the fastest thing you can imagine. Also, someone has to pay for the cloud. Either users will pay for the cloud or the company will pay for the cloud. And what we tried to do at JetBrains, we tried to address these limitations by making this AI code completion feature to work on the user devices. And before going forward, let us ask ourselves, is it even theoretically possible to make this AI feature work on the consumer level devices? And the answer here depends heavily on our expectations on the use case. If we expect our code completion to be able to write the entire method for us, given a method signature, then probably we're in trouble. To do this with a reasonable quality, we will need really large models. And unfortunately, models like this will not be able to work on the consumer level devices with a reasonable latency and resource consumption constraints. However, please consider this example. I argue that this code completion is pretty useful because it saves a reasonable amount of user typing. Although it's much simpler task to generate completion like this. And given it is a simpler task, we can go with much smaller yet smart models to solve this task with a reasonable quality. And the models like this will be able to work with the reasonable latency and resource consumption constraints on the user-level devices. And that is exactly what we call local AI code completion by JetBrains, or officially full-line code completion. It is a local AI that uses a tiny language model that runs directly on your laptop. It is available out of the box in the majority of JetBrains IDEs today. It saves a vast amount of typing for user. It checks the semantic correctness of generated code before it shows the suggestion to you, which makes this feature unique. And it does not require any additional subscription. As I said, we released the feature on April this year, and we got pretty much nice feedback on Twitter, Reddit, some other platforms. According to our internal questionnaire, 80% of our early adopters find this feature useful or very useful. And having this in mind, let us go on and let's start digging into the details, looking under the hood. First of all, this high-level schema. It did not change too much. The only thing changed is that language model now lives on the user's local machine. But since today we are attending a technical event, I suggest to dig a little bit deeper. I promise you there are a lot of fascinating things to explore. So here's the more realistic view of what's going on. And what I suggest doing right now is going block by block, trying to explore some interesting things around these blocks and trying to understand how does this thing works end to end. Unfortunately, today during this 25 minutes talk, I will not be able to cover everything. But I've done my best to pick really the most interesting parts to highlight here from stage, and I'm more than happy to discuss all the rest in the QA session and of course in the couloirs of this conference. So let's get started. What is the first question that you should ask yourself when you are developing a new feature? In my opinion, it is the following. How do I track my progress? How do I make sure that the new feature really improves user experience? To answer these questions, people use online evaluation. And let me describe how do we do online evaluation for full-line code completion. First of all, let's consider the screenshot. What you can see here is full-line or AI code completion, this gray text, and standard IDE completion is drop-down list. And the question is, how do we make sure that adding this full-line code completion really improves user experience? To answer this question, we of course use industry standard, A/B testing. And for A/B testing, we use something called JetBrains Early Access Program. Early Access Program is an opportunity for users to use paid JetBrains products for free, and by doing so, users explicitly agree to be a part of testing environment for new features. And in this early access program, we have two task groups of users. For the first task group, we enable full-line code completion by default. For the second, we disable it. And by comparing metrics between these task groups, we can draw conclusions on whether or not full-line code completion really improves user experience. Let us talk about the metrics that we are measuring in our experiments. We are going to track two types of signals. First of all, it is a positive signal, signifying that users are enjoying new feature. More code is generated. User has to type less to achieve the same result. And the negative annoyance signal, signifying that new feature somehow annoys users. And what we are willing to achieve at the end of the day is maximizing this positive signal while controlling the negative signal, not allowing the negative annoyance signal to grow above some baseline value, which is the value for no full-line code completion test group. And it's worth noting here that if you read some blog posts or papers around AI code completion, you would probably notice that people tend to focus a lot on maximizing this positive signal, while kind of neglecting the importance of controlling of this negative annoyance signal. And by the way, AI code completion could be really, really annoying. I will show you the examples later. And at JetBrains, we're deeply concerned about controlling this annoyance signal, about not allowing the new features to stand on your way. And given that said, let us describe the exact metrics that we use to track these types of signals. For the positive signal, we measure the fraction of code generated, which is the ratio of number of characters generated by IDE, by standard code completion or full-line code completion, divided by the total number of characters that user produced. And for negative signal, we measure explicit cancel rate, which is probability of explicitly hiding the suggestion, by escape, by mouse button, by arrows, whatever. We measure deletion after accepting rate, which is about deleting the entire suggestion after accepting it. And we measure IDE performance degradation, of course. It should never be the case that because of some new feature, overall performance of IDE degrades substantially. And given we have now the main key metrics, let us go on and see what were the final A/B results that we achieved. We observed that fraction of code generated increased by 30 to 100% depending on programming language, which means that for some programming languages, we were able to double this fraction. And the negative metrics did not change, which means that the new feature does not annoy users. After observing these nice A/B results, we decided that yes, full-line code completion improves user experience. And because of that, we decided to turn this functionality on for all users. And that is our approach to online evaluation. Now let's describe the next very, very important block, the block that allowed us to combat this negative annoyance signal, and that is suggestion post-processing. On this slide, you can see several critical reviews for different AI code completion tools. If summarized, people tend to complain that sometimes AI generates syntactically incorrect code that could contain non-existent variables, non-existent methods, etc., etc. And the reason is, of course, LLM hallucinations. So how do we deal with that in case of full-line code completion? For full-line code completion, we show the suggestion only after it was checked by IDE correctness checks, which guarantees that the user will never see semantically incorrect code in full-line code completion. There will be no wrong API calls, no non-existent variables, classes, methods, etc. However, there are of course downsides, and let's discuss them as well. First of all, correctness checks may time out, and if they time out, we have to hide potentially good suggestion. Then there will be no suggestions while indexing for some languages. For example, at Java, code inspections are not available if your project is not indexed, and because of that you will not see full-line code completion if your Java project is not indexed. And actually we had a heated debate inside of our team on whether or not we should guarantee code correctness in 100% of cases. And after a lot of communication, after a bunch of analytics, we decided that yes, we are going to prioritize user trust here, and we are going to do our best to guarantee code correctness in 100% of cases, although we have to sacrifice some amount of potentially good suggestions for that. And this is the first part of this post-processing pipeline. Let's go on and consider the next part. Consider this example, please. This return result suggestion is absolutely correct syntactically, but it's absolutely useless. The second example is even worse. Again, correct syntactically, again useless, but annoying, because these black sort values, in this case, the code that you have already written will get shifted towards right by this suggestion, and it's really annoying experience. And by observing this, we decided that we should employ some smart post-filtering procedure to avoid showing users annoying suggestions. And unfortunately here, language model cannot be used directly because language model hasn't seen users' actions, and language model cannot predict whether user will accept the suggestion. As we all know, language models are trained to generate the next token, and they are good at this task, not at predicting users' attitude towards generated suggestion. But what we can do instead, we can train other machine learning model to predict the probability of accepting the suggestion. And as the features in this model we will use Language models output probability, of course. We'll use length of the context, as well as the length of the suggestion. We will use user typing speed. And we will use entity under the caret, whether it's method, variable, or whatever, and a lot more features. And for dataset, for targets, we'll use early access program again. Early access program is opportunity to use paid products for free. By doing so, users explicitly agree that more logs are collected. Note that code is never collected to the logs, but we do not need code. We need those anonymized features I described and anonymized actions like accept the suggestion, hide the suggestion, etc. And using all this stuff, we can train a model to predict suggestion acceptance using the features that describe the context and the generated suggestion. And then we'll use this filter model to filter out the suggestions that are unlikely to be accepted. After training this model, we deployed it and ran an A/B test. And here are the results. We observed the increase of acceptance rate of full-line code completion by 20 to 50% depending on programming language. And explicit cancel rate, our main annoyance metric, dropped by 50%. And as you can see from this slide, eventually we are able to control this metric to bring it back to the baseline or no full-line value. As you can see here, if we deploy full-line code completion without filter model, the annoyance doubles, which is unacceptable. And by using smart filter model, we are able to control it and to bring this negative metric back to its baseline value. And the price we had to pay for that is drop of total number of full-line code completion selections by 20%. And that is our approach to suggestion post-processing. Now let's go on and let's discuss how are these suggestions generated on the consumer level devices. Model inference. Let us first of all note that language models are not an executables. Language models are just arrays of numbers, and efficient inference of language models is a rapidly developing field. In our feature, we use low-level open-source inference engine called Llama CPP, and let me dig into the details here. As I said, model inference is rapidly developing, and generation time rapidly improves. And I want you to feel the velocity of this improvement. Please consider the histogram on the slide. It is a very same benchmark run on the very same hardware with Llama CPP at spring and fall 2023. As you can see, due to some software improvements in Llama CPP, we have 40% improvement, which is kind of crazy for half a year. And this improvement kind of continues. Actually, today, there are a lot of things happening in this local AI field. Apple is announcing some local AI features. Microsoft is announcing local AI features. Today, I'm describing you some local AI features, and I'm sure we'll witness more and more of that because of this fascinating progress, both in the software side and, of course, on the hardware side. So, Llama CPP, it provides us the most efficient generation, and nice thing, it provides us out-of-the-box usage of GPU on Apple Silicon chips. And we are modifying Llama CPP for our feature, and we are contributing our changes back to open source. And by doing so, we are happy to be a part of this nice progress of open source community in large language models inference. And after inference is discussed, it is perfect time to discuss language models themselves. We train our language models from scratch. We do not use pre-trained models. We use programming language specific models, which means that every programming language or family of languages have their own dedicated model. We use 100 million parameter Llama model with 1500 tokens context size, which is roughly 200 lines of code. It is the amount of code that model sees when generating suggestions for you. The model occupies 50 to 500 megabytes of memory, depending on the actual context size, and that is achieved by quantization of model parameters down to 4 bits. Our models are trained on AWS instances with 8 A100 GPUs, and full training of one model costs us roughly $5,000. And while $5,000 is a reasonable amount of money, it's not crazy. It's not millions of dollars like for large-scale models. And because of that, we can iterate again and again and again. We can really run a lot of trainings to find the best possible training regime to train the best possible models of this scale. And that is our approach to model training, and one of the reasons why do we train our models from scratch instead of using some pre-trained ones. And at this point, hopefully you understand that AI code completion is something very tricky with a lot of moving parts, and we really have to experiment extensively to arrive to the best possible user experience. Online evaluation that I described earlier is a very solid experimentation tool, but it is slow and expensive. We cannot use online evaluation for all our hypotheses. We need to have some hypothesis pre-selection mechanism, and it is offline evaluation. We have two types of offline evaluation. There is evaluation of language model itself and evaluation of this entire generation pipeline with all those syntax checks, filter models, etc. The former is quite standard machine learning evaluation procedure. I do not want to dig into the details there. Let me instead describe how do we evaluate the entire pipeline of code generation. To do it, we use our IDEs in a headless regime. We open some files in IDEs and trigger code completion in random places in a file. By triggering code completion in IDE, the entire pipeline is executed, and we measure some metrics. Metrics based on match between suggested and ground truth code, and latency-based metrics. And we use these metrics to perform hypothesis pre-selection and to proceed further to A/B testing stage with the best performing hypothesis. And here, unfortunately, I have to wrap up this details section due to the time constraints. Again, I'm more than happy to discuss everything in the couloirs and in the QA. And now let me tell about something that made this feature possible. The team. Our team consists of 14 people. 3 of them are ML engineers, focusing mainly on model training. 4 are full stack engineers, including myself, by the way, focusing on making this entire pipeline work better. 3 Kotlin developers, focusing on bringing things to idea. C++ developer, focusing on model inference, half-time QA, project manager, and a team lead. And in my opinion, this structure of 10 to 20 people, full stack, product-oriented team is the best possible structure to deliver features like this. So what are the takeaways of today's talk? Local AI is rapidly developing. You've probably heard about local AI by Apple, by Microsoft, today by JetBrains, and there will be more and more and more in the future, I'm pretty sure. I hope I convinced you that making good AI code completion is much more than just deploying a good language model, although a good language model is absolute prerequisite for good AI code completion. Using local AI models instead of cloud makes your development process somewhat more secure, and it is still possible to do good AI code completion based on local models. You can try it out at JetBrains IDEs. And here's the very last thing I want to show you. It's arXiv paper on full-line code completion. Although it's a bit outdated, as you can see, it contains much more technical details than I were able to share with you here during this 25 minutes talk. Here I would like to thank you very much for your attention, and I'm happy to take some questions.
Hi.
Hi.
Any plan to fine-tune this, let's say, probably we can call it small language model on the code of each individual user, so as to have some more personalized suggestion and maybe be more compatible with the code of each developer?
It's a nice question. Even we had some proof of concept that it yields some kind of good results, but still, if you speak about fine-tuning on a specific code base, the kind of growth in the quality is not as big as for large models that provide multi-line code completion. And because of that, the main focus, if we will move towards that direction, will be in fine-tuning like several billion parameter models which work in cloud on the user's code base.
Hello, thank you for a fantastic talk. So I wanted to ask, what kind of data do you use for training? Like how do you take your code to train? And also, so this is your purpose-built model, not pre-trained model. So I'm also curious about how do you construct like a prompt for your model? How do you do it in order to get the best results here? Thank you.
That's a good question. Speaking about the data, it's data from public repositories, which with this suitable license that does not forbid to use it. And about the prompt construction, it's really interesting question. You, at the prompt, you of course have your prefix, the code before the cursor. It's obvious thing. Also, you have some meta information about what is the current file, what is the extension, etc., etc. Also, you have some code snippets from other files. There is a kind of RAG step when we try to retrieve snippets that could be helpful to generate code completion and also put it into the prompt. And also there is something called fill in the middle. I didn't include it in my talk due to the time constraints. It's a technique to allow the model, roughly speaking, to see the right side. When you put a caret, you probably, while generating, you want not only see the prefix, but also see the suffix. And this technique allows you to see the suffix. So generally, these techniques allow us to construct prompts. Some of them are still kind of experimental and not enabled in all of the IDEs, but generally it's pretty much pretty all that we are doing.
Thanks for a great presentation. A quick question. So do you train one model for each ID, so for different languages, or is it like programming languages, or is it only one model?
It's a good question. We started by training per language models, but after that we started to group it not to kind of occupy a lot of memory on the user side, because if you are developing, for example, web application, you will have TypeScript, you will have HTML, and probably you do not want to have like separate models for that. And we have some heuristic to make these groups of languages that share the same model. So it's not exactly one model per IDE, but kind of close to that.
Yeah, okay. Another question is, what is the inference time in the end, like from when the user kind of stops typing to when he sees
inference time on the median, it's like 300 to 400 milliseconds. And it's not inference time, it's time to show. So inference time is slower, obviously.
Thanks for the presentation. I have a question related with different type of tasks. For example, now you have autocomplete, but maybe in the future you want to generate doc strings or whatever. Do you think that should it be different small models for each task, or should we have in the future a big model with general purpose tasks?
It's hard to say. I think that it's a matter of experimentation.
Okay, thank you.
Okay, thank you everyone. So if there are any further questions for Daniel, you can ask him during the coffee break, and we will resume our talks in the Lavender Hall at 4. Thank you.